Okay, we have looked at MJO, or more generally interseasonal oscillation theories already, but this paper by Shannon Zhang and co-authors provides a nice summary which I will go through here and re-emphasize some of the points. So in situ data now, field campaigns like Dynamo and Year of the Maritime convection and lots of satellite data have actually increased our understanding of the vertical structure of heating, the relative phasing of air-sea interactions ahead of MJOs, behind MJOs, moistening processes, boundary layer versus pre-tropospheric processes, and so on and so forth. I am aware that there is a howling wind sound that is coming through in some of the podcasts, but I think I checked and it's quite audible. I leave the window open because otherwise it gets too hot and humid and I don't like to run the AC. So hopefully it's very clear. Okay, so here summary of each theory discussed in this section. Theory, essence of the theory, and observational modeling and evidence given in these papers, which we will not go through. So this is called a weak temperature gradient moisture mode. Basically, weak temperature gradient is the observation that in the tropics, once you're in the free troposphere, the temperature gradients are very weak. And considering the very strong dynamic heating that occurs because of convection throughout the tropics, what is the dynamic mechanism which is maintaining this fast timescale weakening of the temperature gradient? And moisture mode is basically a terminology that says any mode that where moisture is a key ingredient can be called a moisture mode. So MJO has been argued to be a moisture mode in that sense that moisture and the moisture convection feedbacks, convection dynamics feedbacks, and the processes of moistening are very critical. So Sobel and Maloney have proposed this, and then Adams and Kim have looked at it. And the essence of this is that the moisture convection coupling is a key. So many of the models show that MJO-like features can be generated with waves in a dry atmosphere, but moisture seems to be key for explaining the propagation speeds and so on. Moisture advection is important for propagation, so as opposed to the weak temperature gradient and the balances that go with that, you still have strong moisture advection. If temperature gradient is weak, then obviously temperature advection is weak. So cloud radiative feedbacks cause growth and determine the horizontal scale. So it should be made clear that every theory has to explain two key ingredients of MJO. One is that the propagation speed is weaker than the free Kelvin waves, eastward propagation. So we introduced the concept of convectively coupled equatorial waves, which give you an excuse to say why they propagate slower than Kelvin waves, but obviously that's kind of a catch-all term. So you still have to explain the speeds properly with the processes. The second key feature of the MJOs is the planetary scale. So there are balances involved. For example, the clouds associated with the planetary scale of the MJOs, other than the convective deep convection and the rainfall phase, rainfall structure associated with MJOs, the clouds actually trap the outgoing long wave radiation, which has to be balanced by the rising motion, expansion, moistening of the troposphere, and the cooling associated with that. So these kind of cloud radiative feedbacks are required for growth of the MJO and determining the horizontal scale. So that's the WTG moisture mode. Lots of details there, but this is just a summary. Vichy moisture mode is proposed by Fuchs and Raymond over several papers. Moisture convection coupling is key here. Vichy determines propagation, growth, and scale selection. Cloud radiative feedbacks provide additional growth. So, if you remember, Vichy wind-induced surface heat exchange is essentially relying on the fact that MJO-related winds anomalies are easterlies to the front of MJOs and westerlies behind, and the background winds of easterlies are assumed to enhance surface heat exchange ahead of the MJO to increase enthalpy into the atmosphere, moisture loading, and so on. But observational evidence isn't so clear that the surface heat exchange and surface moistening processes are a big part of MJO once it's organized and is propagating eastward. And as we mentioned before, the background winds are actually weak westerlies over the Indian Ocean and the West Pacific, where Vichy actually doesn't explain the eastward propagation. So the moistening ahead because of Vichy is not very clear. There are also other nonlinear Vichy and other models, but observational evidence is found in these papers for supporting the Vichy moisture mode, which means the moisture is still a key player in this model as well. BLQE is boundary layer quasi-equilibrium model, which is proposed by these people, where convection adjusts to maintain the boundary layer quasi-equilibrium. So moist static energy evolution is key in this model for explaining the eastward propagation and why convection should go eastward. So the moist static energy from the boundary layer equilibrium, quasi-equilibrium, is critical for creating instability ahead and creating conditions for propagating eastward. Cloud radiation feedback determines the growth of the convection, and Vichy provides the eastward propagation again. So it's a combination of BLQE and Vichy in that sense. But as I said before, lots of observational evidence and process understandings have allowed multiple models to evolve, but obviously there is no consensus because each one has a drawback in terms of fully explaining the MJOs and whether they can explain all of the MJOs or are key for the observational evidence that is found in specific MJO events. Okay, so I'm not going into the details of what are the deficiencies or limitations, drawbacks of each model, but the paper provides the details, at least the key points in what is missing in each model. For example, the weak temperature gradient assumption is from empirical evidence, but is it necessary for the fundamental MJO, and are the moisture modes necessary, or a dry atmosphere can also produce interseasonal variability that is similar to MJO? It turns out that in fact winds do have interseasonal variability that are not related to moisture moist processes, so that has to be explained as well. And boundary layer, again, as I said, the surface heat exchange and the moist static energy of the boundary layer, for example, advection of moist static energy from elsewhere, can still be a critical role in MJOs, so BLQE may not be the complete model as either. The trio interaction is something that emerged out of the older Kelvin-Rossby wave theories. It emphasizes the boundary layer frictional moisture convergence. We called it frictional convergence instability in the model we looked at in some detail, because that chapter was written by Bin Wang, and obviously Bin Wang is the one that is proposing the trio interaction theory as well. So here the frictional convergence instability to the east of the MJO convection center determines propagation and growth, and moisture convection coupling provides the slowing down of the waves, so to explain the observed propagation speed, and it doesn't necessarily need cloud radiation feedbacks, but it is included in the model, and these are the papers that provide some observational evidence that is consistent with the key processes assumed here in terms of the moisture convection feedback, frictional convergence, and moistening, and the coupling, moisture convection coupling to slow down the MJOs. Okay. A skeleton model of Maeda and Steckman basically emphasizes the multi-scale interactions. So MJO is assumed to be an envelope of synoptic waves and mesoscale systems. So that gives you the multi-scale interactions. MJO propagation here is because of the interaction between low-level moisture and synoptic scale wave activity. Okay, so there are mathematical formulations in the model which take these multiple interactions to try to produce the MJO amplitude, growth rates, eastward propagation, and so on. So the main emphasis here in the skeleton model is on the synoptic waves and mesoscale systems and the multiscale interactions between them. Again, this model also has some limitations, even though obviously it has to fit some of the observations, because all theories try to fit the observations for some major features they consider important a priori. So none of them is a full-scale GCM or primitive equation model. They are all models that are using some kind of idealization and simplification. The gravity wave model assumes that MJO is an envelope of eastward and westward propagating inertiogravity waves. Remember the two-day westward propagating waves were the inertial gravity waves that we mentioned before with a forward tilt. This model doesn't require Rossby waves and Kelvin waves. Instead, it says that the eastward propagation is determined by the faster wave speed of the eastward propagating inertial gravity waves. Of course, Kelvin wave is a gravity wave as well, but in the wave frequency phase diagram, the inertial gravity waves are separate from the Kelvin wave. And in this model, the horizontal scale is determined by interaction of waves and convection. So convection provides the eastward selection of eastward propagation. Asymmetry between the waves, eastward and westward propagating inertiogravity waves, is provided here by the beta effect, which determines the propagation direction and speed. But that means this also restricts the system to the tropics, where the beta effect is important for these inertiogravity waves. And it's not clear that the observations show westward, eastward propagating inertiogravity waves, and there are arguments made about whether MJO has a westward group speed or energy propagation, and so on. Nonetheless, there is some observational evidence, and the authors of this paper that we are discussing argue that this theory requires more investigation because it has some interesting new ideas. Nonlinear solitary waves, so Yano and Joe Trivia and others. MJO is strongly nonlinear solitary Rossby wave. Okay, it's not a wave train, it's just a solitary wave. MJO is explained by dry dynamics to first order, so moisture mode is not the main grounding theory here. Nonlinear vorticity advection explains propagation. Okay, so this is not so clear because there are other papers by Chidong Zhang which show that potential vorticity in the MJOs is actually related to the diabatic heating. So in that sense, moisture mode is important, even though this one can rely on dry dynamics alone. And vorticity advection doesn't seem to be necessarily a big player in MJOs as such. Large-scale modons exhibit longest durations. So this is a theory that fits some of the observations that are found here. Large-scale convective vortex. MJO is an eastward propagating pair of Rossby gyres. Propagation is due to strong low-level vortex stretching. So if you assume vorticity conservation, stretching of the vortex requires certain flow adjustments. So deep convection can indeed do vortex stretching, and it can then produce deep convection to the east of these Rossby wave cyclones. So this is going to explain some of the observed features as well. Just to conclude this brief summary of the main MJO theories, modern theories, here is a comparison of role of moist processes in each of the theories discussed here. So it's looking at convective coupling, whether it's essential, prognostic moisture, whether it's key or not, moist processes, whether they are key to propagation or not in terms of slowing down the propagation speeds, moist processes, whether they are key to MJO growth, and cloud radiative heating, whether it's included or not. Remember that models tend to do the wrong propagation speed, weaker amplitude MJOs, so these MJO growth and propagation and moisture processes are all critical, especially in terms of feedbacks between convection and moisture. So looking at WTG moisture mode, Vichy moisture mode, VLKV mode, trio interaction mode, skeleton mode, gravity wave model, nonlinear solitary wave, and large-scale convective vortex, all of them have convection coupling with moisture. Moisture processes are critical except the nonlinear solitary wave. So basically everybody needs moisture to be a key ingredient, and most of them require moisture to be a key prognostic variable and not a diagnostic. So it's not just a passive tracer, it's an active tracer in that sense. But these three wave models, gravity wave, nonlinear solitary wave, and the large-scale convective vortex, do not have moisture as a key prognostic variable. Moist processes are key in propagation for all of them except for the gravity wave model and the nonlinear solitary wave model. Moist processes are critical for MJO growth in all models except the skeleton model, which depends on this multi-scale interactions, so it doesn't need moist processes for MJO growth. It can do upscale transfers of momentum and energy by just these multi-scale interactions. Gravity wave model doesn't need it either, and non-linear solitary wave doesn't need it either. Cloud radiative feedbacks are in the top 4 models, and the bottom 4 models do not require cloud radiative heating. Okay, so obviously that means the observations will keep improving and process understanding will keep improving, and GCMs will keep producing their version of MJOs which are diagnosed for these key processes in terms of their propagation speed and the planetary scale, which is of course done after filtering to the intraseasonal timescales, and then the details of whether it's a moisture mode, whether there are convection moisture feedbacks, cloud radiative feedbacks, and so on. So this is a two-way process where you want to improve the GCMs with specific convection processes like convective momentum transport, dilute plume approximation, and other things which in fact do improve MJOs, and these process models that we discussed, where understanding the key processes becomes easier, especially when compared with observations. So these processes will go on together. Okay.